Okay, so welcome everybody to today's seminar on automorphic forms. So it's a pleasure to welcome Elisa Garcia from Université de Neuchâtel. Sorry,
No.
and she will talk about the conductor of Ciani plane quartics. Yeah, so Elisa, please.
Thank you very much. Thank you very much for the introduction and thank you very much for the invitation. It's a pleasure to be talking here today. So I want to tell you about the conductor of Ciani plane quartics. Unfortunately, I won't mention that much about automorphic forms, but I hope also to I hope that you would enjoy anyway the topic that I decided to bring to you. So maybe some of you are not familiar with the conductor of a curve or the Jacobian of a curve, or you don't know what is a Ciani plane quartic. So, I really want to do like an easy motivation. And I'll give all the definitions, what is a conductor, and well, I'll try to motivate why Ciani plane quartics are important. Okay, so in order to do that, let me start a little bit with the classification of curves by genus. So let's say, well, before that, maybe I should say, even if it is written, insist on it. This is a joint work with my three collaborators, Irene Bau from the University of Ulm, Nirvana Coppola, that was in Amsterdam during the time that we did the paper, and Anna Somoza, that was in Rennes. Okay, so curves. So when we look at curves and we want to kind of classify them by complexity, let's say, the natural invariant to look at it is the genus. So let's say that curves of a small genus are easier than curves of large genus. So for instance, genus zero curve, they are conics. And basically, when you look at them over the algebraic closure, they are all isomorphic. So, there is not too much fun. So I'm trying to get the, is this working? Yeah, here. So all the genus zero curves, they are isomorphic and they are conics. For genus one curves, typically we think about elliptic curves. But elliptic curves is when you fix a rational point. Like more generally for a genus genus one curve, you can think about an equation like this, where the degree of f is 3 or 4. And in this case, the moduli space, for elliptic curves, is dimension 1. So, you have still kind of a family, but it's still like a small dimensional subset. For genus 2 curves, again, you can write your equations of this shape, y squared equal to f of x. Actually, if you think about it, the genus zero case is the same thing, right? Because for the genus zero case, I wrote like the homogeneous equation. So if you make z equal to 1, you see that all the genus 0, genus 1, genus 2 curves, they look like hyperelliptic ones. So they are given by an equation y squared equal to f to the x. And in this case, the dimension is 3. And now we move to genus 3. And I have to say that I really like genus 3 curves. And if you look at my papers, my PhD thesis, my habilitation, like in France, like to become a professor, like it's always around genus 3 curves. And, I always get this question, why genus 3 curves? And this is kind of my canonical question, is because somehow genus 3 curves, they are like the most simple curves that they are still kind of generic, in the sense that all genus 3 curves, they are not anymore of the form y squared equal to f of x. That's it. They are not hyperelliptic curves. So genus 3 is for the first genus for which you find non-hyperelliptic curves. In genus 3, the curves that are not hyperelliptic, they are given actually by plane quartics. And actually it's like the generic case among the genus 3 curves. The moduli space has dimension 6. And as you can see, the hyperelliptic locus has only dimension 5, it's codimension 1. So the generic genus 3 curve is given by a plane quartic. That is actually the canonical model of the genus 3 curve. By the way, I usually speak quite fast, but please don't hesitate to interrupt me if you have any question or you want me to explain something again. So yeah, I was saying that for genus tree curves, we have like the moduli space. I try to do here like a to do like a draw of the moduli space in which you have the hyperelliptic locus that is codimension 1. And then you have like your curves that they are in the moduli space. Those curves in the moduli space, they are parametrized by invariants. So the invariants for genus tree curves, they are called the Dismer on invariants. And they are basically like, if you never worked with invariants, you can just think about them as polynomials on the coefficients of a generic plane quartic. So a plane quartic has 15 coefficients. So it's just a polynomial on the coefficients in such a way that this polynomial, even if you make a chain of variable in your plane quartic, this expression on the coefficients is going to remain invariant. This is why they're called invariants. So basically they describe the isomorphism class of the curve. And this is why they parameterize the moduli space, the points on the moduli space. And as I said, there are 7 algebraically independent invariants, and then there are 6 algebraic dependent ones. So basically these extra 6, once that you fix the first 7, you only have like a finite number of options for all of them. And now as a kind of an exercise to see if we understand what is happening here, look that I said that the dimension of the moduli space is 6, but the number of algebraically independent invariants is 7. Where is this 7 and this 6 coming from? Well, it is actually coming from the fact that those invariants, you have to look at them like in a projective space. So basically these 7 algebraically independent invariants, they are given like a dimension 6 space. So what else? Now I can say something about the field in which these invariants belong and the field over which a curve is defined. This is going to be like a game between geometry and arithmetic. So let me tell you more about this. Now I'm giving all these details about genus tree curves because then I'm going to give the definition for a Ciani plane quartic that is going to be like a specific family inside this moduli space. And somehow I also want to try to convince you that these mirror own invariants, even if they are like really useful, they are kind of complicated. So sometimes it's better to work with other things. So what we get is that the Dismeron invariants, they parameterize the point in the moduli space. So the field of definition of this point given by these invariants, so the invariants, they are defined over a field, this is the field of moduli. The point is defined over that. And those invariants, they give you the K-bar isomorphism class, right? Like two curves, they are isomorphic if and only if they have the same invariants. So somehow these invariants, they are really related with the geometry of the problem. Now, a natural question, and we'll see that unfortunately it is not always answered by a yes, is that the field of moduli is not necessarily a field over which you can define the equation of a curve with the given invariance. So, I mean, this is something that, for example, I mean, I guess that if this is the first time that you see in this general way about curves and invariants, maybe this is a little bit complicated, but maybe you can think about elliptic curves. The J invariant, you can always give an equation of an elliptic curve that is defined over the field that the J invariant is defined. But unfortunately, like for generic curves, this is not true anymore. In general, the field of moduli is only contained on the field of definition of the curve. And the field of definition of the curve, well, besides that you can have twist of the same curve, I'll come later to the concept of twist. More or less, they give you the K isomorphism class. It's kind of an arithmetic information. This is again something that is like, in my research, I always play with this at the border between the geometry and the arithmetic of the curve. And today we'll play also at the in the middle of these two topics. Anyway, there is a result by some mathematicians, Larcier, Robeta, Retzenthaler, and Seisling in 2014 that proved that for plane quartics, so here white is a plane quartic, if the automorphism group is big enough, then the field of moduli is equal to the field of definition of the curve. So we have an equality at the level of fields in this case. And well, this is also to motivate a little bit that then we are going to look at curves with an automorphism group a little bit big. And the thing is that if you look at the stratum, the different strata that you get for the moduli space of genus 3 curves, non-hyperelliptic ones, by automorphism, so the largest one, meaning the one with the largest dimension, is actually the one of Ciani quartics. So, I mean, this is, for instance, an interesting fact for which we want to look at these quartics. I haven't given the definition yet of Ciani quartic, but don't worry, I'm coming to that. Also, Ciani quartics, as you will see, they have another interesting properties because, I mean, we want to study something that is still generic enough, even if we are making this restriction about assuming the curve to have extra automorphisms. And I mean, as we saw before, like all the hyperelliptic curves that they are given by an equation of the form y squared equal to f of x, they have been like really studied by many people, and also kind of the natural generalization of those ones that are the ones called super special curves, that they are the ones that they are given by an equation like this, y to the L equal to f of x. Being able to write a curve in this way is equivalent, I mean, at least over an algebraic closed field, to have a cyclic map from your curve to P1. So for Ciani quartics, this is not the case. And I mean, this makes them really special because, I mean, I'm going to tell you now more things about Ciani quartics. And basically, they are like the first curves for which we have some results and that they are not a cyclic, they don't have a cyclic map to P1. Okay, so now I can give you the definition. After speaking for a long time, I can present you the object, the family of curves that I'm interested and that I want to discuss today. So what is it a Ciani quartic? A Ciani quartic is a non-hyperelliptic curve of genus 3 together with a subgroup of its automorphism group here that is isomorphic to the Klein group. So the Klein group is two copies of the cyclic group of two elements. And in such a way that when you do the quotient of the curve by the subgroup, you get another curve. And when you look at the genus of this curve, you get a genus 0 curve. You get a P1. Such a subgroup is called a Ciani subgroup. Well, you will see that this is kind of the abstract definition that can be understood like, okay, it's a genus 3 non-hyperelliptic curve with a big automorphism group. But like this choice of the subgroup, we'll see that will help us to construct like a specific equation for the curve. So let's play a little bit like with this subgroup and to see what we get. So let me call the elements of the automorphism group like this. So 1 is the trivial one, and sigma 1, sigma 2, and sigma 3, they are the order 2 automorphisms in the subgroup. If you do the quotient, it can be checked that with these conditions, the quotient of the curve by each of these elements is actually an elliptic curve. Because, I mean, if you do the quotient by all B, then you are asking to get genus 0. But if you do the quotient by only one of the automorphisms, then you get an elliptic curve. So basically, you get a diagram like this one. So here you have like your genus 3 curve. Sorry, because the screen is not flat. I don't really have that much control. You get your genus tree curve, and then you get like degree two maps to elliptic curves that they have genus one, and then you get degree two maps when you do the quotient by all the subgroup to P1. And if you look at these morphisms, you can look at the ramification. And actually, what is funny is that if you look at the ramification from white, your genus tree curve, to P1, you get 6 points. So, I mean, basically, that is kind of the same thing to give the Ciani quartic by an equation, the plane quartic, that given P1 with 6 points, that they are going to correspond to the ramification point, but somehow they are like, you have to pair them up. So you have 2 points here that go together, other 2 points here that go together, and other 2 points here that go together. And you can see that they are given by the ramification type that I gave you in this diagram. Okay, so this is a Ciani quartic. But now I said that for a Ciani quartic, I make a choice. I take this subgroup. But I mean, is the automorphism group of the Ciani quartic just equal to this subgroup? Can it get bigger? And actually, the answer is that indeed, you can get a larger automorphism group. So you can look at the stratification of Ciani quartics, of the family of Ciani quartics inside the moduli space of genus tree curves by automorphisms. And then you get this nice diagram. So basically, as I mentioned, in general, you get like a dimension 3. This is like the generic case. But then you can get extra symmetries, which means extra automorphisms. And you can get like a subfamily of codimension 1 with automorphism group T4. Then codimension 2, you have like 2 different families, one with an automorphism group of 16 elements, and another one with a symmetric group of order 24. And then you can like even specialize further the families for like a given values of the parameters. And you get like some points because now it's going to be dimension 0. And actually there is a single curve for each of these larger automorphism groups of order 48, 96, and 168. So let's say that those curves, they are like very, very particular ones. There are 3 of them that they have like a big automorphism group. And actually, I mean, I can tell you this one, the one with the largest automorphism group is a Klein quartic. That is the one with the, I mean, with a big automorphism group, lot of symmetries. It is actually what is called Hurwitz curve, because the automorphism group in this case has cardinality exactly equal to the Hurwitz bound, that is 84 times the genus -1. So it's like a very special curve. For the automorphism group of order 96, we get this correspond actually to the Fermat quartic. And then for this one, the last one that is very special, you get a curve that is also a Picard curve. So this one is like super special with L equal to 3. So, well, very special curves. But I mean, we'll be interested in the generic case. That is a case in which the dimension is 3, and in which you get that the automorphism group is going to be actually precisely equal to the Klein group. So to the product of 2 copies of the cyclic group of 2 elements. And this motivates the following definition that says that a Ciani quartic is called non-special. Well, I'm defining a special in the same definition. If there is a unique Ciani subgroup. And actually, we can check that this is equivalent. The fact about being non-special to having that the automorphism group is precisely isomorphic to the Klein subgroup. So I'm giving this definition because, like, well, you will see that for my results later, I restrict myself to the non-special Ciani quartics. I mean, it's not that what we do doesn't work in general, it does, but it's just that you will see like the computations become much more complicated. So we'll assume the curve to be non-special. And in this way, we can kind of forget about the subgroup because it's uniquely determined. If you want to study a Ciani quartic with a larger automorphism group, then you have to be like fixing all the time, like precising which one is the Ciani subgroup. Okay, so now let's go with the equation, because I've been talking about Ciani plane quartics now for a long time, and I haven't given to you the equation. Okay, that is like the easy way to play with them. So definition, a standard model, or what we call a standard model for a Ciani quartic, is a model of the curve that looks like this, like the equation that you have here. And in such a way that the choice of the subgroup V, the Ciani subgroup, actually corresponds to this symmetry, to, well, basically multiply the variables by -1. And I mean, it's easy to check that the curve, the equation that I showed you here is invariant under the action of this transformation. So this transformation defines an automorphism of the curve. Okay, so maybe I could have started by this. So this is not like the abstract definition. I could have said a Ciani plane quartic. It is just a plane quartic that it is isomorphic to a plane quartic that looks like this one. But if I did it in the way that I did it, it's because of the field of definition. If I only care about the geometry, then this definition would have been okay. But if I do care about the arithmetic, and I do, then it's better to give the definition that I gave you. That is just the non-hyperelliptic genus tree curve with the subgroup. Oh, I see that there is a comment in the chat. Oh, yes, exactly. So this is where we are coming here. It's precisely the Galois action, which is giving the field of definition. So yeah, let's go for it. So look at the lemma. The lemma here is basically now saying I have the Ciani quartic, so I have my genus 3 non-hyperelliptic curve and the choice of the subgroup. My curve is defined over a field K, and the subgroup too. And if you think about the special case, the subgroup is unique. So what I mean is like the sigma V is equal to V, but maybe the elements of V, they are defined over a larger extension, but then the conjugate ones are the other automorphisms. And then what you can prove is that there exists a Galois extension L over K with Galois group, a subgroup of the symmetric group of 3 elements, such that your Ciani quartic defined over K has a standard model defined over L. And the proof of this lemma, you can do it like in a different way. You can just look at the ramification as I saw here. And I mean, because the curve and the subgroup is defined over K, the morphism is defined over K, so the ramification points here have to be conjugate. But you can even think at an easier way. That is like you look at the automorphisms, of your plane quartic, because the plane quartic is a canonical model of the genus 3 curve. So they are given by matrices. So basically the only thing that you have to do is diagonalize the matrices. So the matrices that allow you to diagonalize the automorphisms, that means to put them in this shape, in the shape that we describe here of the automorphisms for the standard model. That transformation gives you precisely the equation of the curve, a standard model, and they give you the field L that corresponds to the basically to the field of definition of the ramification and of the elements in V. the single elements in the subgroup that you choose. Okay, so now I'm going to introduce Ciani invariants because, I mean, I told you, like, for plain quartic, generic non-hyperelliptic genus tree curves, the dimension of the moduli space is 6, and you have, like, all these Meron invariants, but they are, like, quite complex. It's not easy to work with them. And now we are focusing on a smaller family that is only dimension 3. So, like, a natural thing to do is, like, to define, like, new invariants, or like particular invariants only for this family, not for all plain quartics. And this, like, we prove it in a previous paper with my co-authors in this paper plus 2 other members. And we computed, like, the generators for the invariant algebra of these curves. And basically, well, they are the 4 invariants that I give you here, like by these formulas. So the small and capital ABC, they correspond to a Ciani quartic given by a standard model. Now, if you have a plain Ciani quartic that is not given by a standard model, the only thing that you have to do to compute invariance is that you just find a standard model given by a chain of variable with determinant 1. And then you use that standard model, the coefficients of that standard model, to compute invariance. And yeah, basically what you have is like 2 Ciani quartics with the choice of Ciani subgroup. They are isomorphic if and only if they have the same invariance. But again, you have to look at them in a projective way. This is why even if it is dimension 3, you have here 4 invariants. They are algebraically independent. And the number, I mean, you see that there is here like a 3, 3, 3, 6. This is actually the weight of the invariants. So basically what we have is like the weight of the last one is the double of the weight of the other 3. So you can think that I could have written 1, 1, 1, 2. But no, I like to write it at 3, 3, 3, 6. And maybe this is going to be my only opportunity to talk about at least modular forms and not automorphic forms. If you look at this invariant, so if you take the Ciani quartic as complex curves, and you look at them, at their Jacobian inside A3, the moduli space of principally polarized abelian varieties of dimension 3, then the invariants can be pushed forwarded as Siegel modular forms. And then this 336 is related to the weight of these Siegel modular forms. So, well, I mean, it's not important. The only important thing, if you want, for the talk today is that when you look at those invariants, like forming a projective point that gives you the isomorphism class of the curve, well, the last one, you know that the weight is the double of the weight of the other ones. Then, in terms of those invariants, you can write other invariants, but I mean, they are not like algebraically independent. They depend just on those ones. So one of them is, for instance, the discriminant of the curve. So for the discriminant of the curve, we have this expression. So very soon, I'm going to start to look at the reduction type of a plain quartic. So what do I mean for the reduction type? Maybe this is a good moment to say it, because I didn't say it before. I'm just talking about a field, like whatever the field, but actually it's not true. Like, for instance, also for those invariants, to really give the isomorphism class, we need to assume the characteristic of the field to be different. Sorry, as I told you, I cannot write very well with the screen in vertical. Characteristic different from 2 and 3. And you can think about any field, but very soon, in my mind, I'm going to be working all the time over QP, because basically I'm going to be thinking about my curve defined over Q or over a number field, and then I'm going to do the reduction modulo P. And basically, I'm going to start working with a smooth curve. So the discriminant is different from 0. But then I'm going to be interested in seeing or in studying the primes that divide the discriminant. So basically the primes for which at least the model that we are using for the curve has bad reduction, and then to see closer what is happening in this case. Okay, so I mean, I'll go later with that and more details. Okay, so you can define the discriminant to be this product of elementary invariants. You can define the invariant P, that is the sum, that it will play a role later on. You can define the invariant Q, that again will play a role later on and is this combination of invariants. Well, there is a new invariant I here that you have the definition here again. It's just a polynomial on the other invariants. I can also define a polynomial P, like this Gothic P, in such a way that the coefficients of this polynomial, they are again like some invariants as the ones that I defined before. And I'll call the roots of this polynomial Gothic A, Gothic B, and Gothic C. And well, they will play, as you will see very soon, also an important role. But maybe to come back to the invariant Q that I have here, we can mention like two important properties. The first one is that actually this invariant Q is the discriminant of the polynomial P Gothic that I defined here. And the second property that is maybe the most interesting right now is that actually it describes when a Ciani plane quartic is special or not. We get that the Ciani quartic gets extra automorphisms if and only if Q is equal to 0. So if you look at the stratification that we had here, it's very easy. So everything that is below here has Q equal to 0. So this is, if you want, the codimension 1 condition to describe this subfamily. Okay, so now I said enough about Ciani quartics. Now you know how they look like. You know that we have invariants for them. And I can move to the two things that I want to study about this family. The first one is the stable reduction that I'm going to introduce now. And the most important one, because the stable reduction we studied in a previous paper, is the conductor. But in order to understand the conductor of the Ciani quartics, we'll need to understand the stable reduction. So what is the stable reduction? Like, I mean, maybe you already know about the stable reduction, but I guess that not everybody knows. So, I mean, I would like to at least give like an intuitive definition. So the first thing about the reduction of a curve is that actually when you say, oh, I consider the reduction of this curve, it's not something that is like totally intrinsic to the curve. It depends on the model. And I'm going to show you now some examples. It depends on the model. Like, I mean, I can give like a very naive example maybe before. Imagine that you have like a nice curve given by one equation that modulo 7, let's say, you still get a nice curve. Okay, very good. And now imagine that you do something very naive that is multiplying by 7 the equation of your curve. Then, well, I mean, in characteristic 0, if you want over the rationals, this is still a fine curve. You are just given the same equation. But now, if you do the reduction of this equation, you get 0. So, I mean, you get like the, the 0 ideal. So, I mean, you get like a very bad reduction of your curve, like somehow the curve disappears. So, I mean, just to say, this is like a extreme case. We'll see some examples now in which the reduction really depends on the model. So then when you have a curve given by an equation, you would like somehow to associate to it kind of a canonical reduction. Like when we say the reduction of a curve, like you are talking just about a precise thing. And the thing is that among all the models that you can take of your curve and the reductions that they produce, there is a model that is essentially unique in such a way that the reduction that you get is like the best reduction that you can get. And what does it mean, like the best reduction that you can get? So, I mean, it's the one with the less singularities. And the precise definition is that there is like a unique model, essentially, for which the reduction, it is a stable curve, what it is called a stable curve. So what it is a stable curve? It is a curve that at worst has double point, well, that is connected, at worst have double points as singularities. And then there is this technical condition about having a finite automorphism group. And basically this translates into saying that if you have a genus 0 component, this genus 0 component has to intersect at least the rest of the curve at 3 points, because otherwise the automorphism group would be infinite. So, I mean, I don't know, you want like, this is an example of a stable curve. Imagine that this is like genus 1, let's say, and you have a node. Another example is that if you have like something like this, and all those, they are a straight line, so genus 0. But like all these genus 0 components, they are intersecting the other ones in 3 points. So the automorphism group is finite. So those are examples of a stable curve. So basically, to every curve of genus greater or equal than 2, you can associate what is called the stable model. That is this model that when you do the reduction, you get the stable curve. Meaning that even if you get bad reduction, you get like a controlled bad reduction in this way. And maybe it's a little bit unrelated with the things that I want to say today, but I mean, this is really nice because those stable curves, if you add them to the moduli space MG, so to MG, the moduli space of smooth genus G curves, it is actually non-compact, and a way of compactifying it is basically by adding the stable curves. So studying the stable curves is interesting because it helps you to understand the geometry of the moduli space of curves, for instance. So yeah, I mean, one of the possible compactifications of MG is by adding the stable curves. This is what Deligne and Mumford did. So I mean, this is, for instance, one motivation for being interested in computing like the reduction type of a curve. For me, the reduction type means like the special fiber of the stable model. So like this best possible reduction that you can get. Okay, so some examples. You get here, for instance, this first equation that I give you. So I called pi the, yeah, because I mean, I told you, oh yeah, in my mind, I'm almost all the time, because I like the arithmetic, thinking about QP, or even better, like set P. Like my equation is defined over set P, and then I do the reduction modulo P. But actually you can take any discrete valuation ring and then fill. And then I call pi the uniformizer. So I'm going to do basically the reduction modulo pi. So if you look at this plane quartic, that is isomorphic to the Fermat quartic, if you do modulo pi here, you get something that is bad reduction. But actually, I mean, here is very easy to do a chain of variable for which you get good reduction. The only thing that you have to do is divide the variable set by the fourth power, the fourth root of pi. Then pi disappears and you get the Fermat quartic. And if the characteristic is different from 2, you get a nice curve. So actually you have like good reduction for this quartic if you take the right model. The potentially here means that you may need to get to consider a field extension, because you have to divide set by the fourth root of pi. Another example is this quartic. This is a Ciani quartic too. And in this case, if you look at the discriminant, you get that there is a pi, so you have bad reduction. But actually what happens here, and this is very interesting, is that you get potentially good hyperelliptic reduction. So, I mean, this is nice. As I told you, genus 3, and this is why I like genus 3, really, that this is like the smallest generic case and the first one in which you see this kind of things. This is the first genus for which you see that you can have hyperelliptic reduction. So you start with something that is non-hyperelliptic, and then you will get a hyperelliptic, a nice meaning a smooth hyperelliptic curve. And then, for instance, you get another case. Here, I gave you another example. This Ciani quartic. Here, you get a pi in the discriminant, so it's bad reduction for this model. But actually, whatever the model you get bad reduction. And this was actually like in a paper with some collaborators, with Larcière, Liu, and Retzenthaler, that we characterized when you have a plain quartic and you look at the primes that appear in the discriminant, when you actually have potentially good quartic reduction, when you have potentially good hyperelliptic reduction, and when, whatever you do, you get bad reduction. So there is no way to get a good model. And then what I did, because of course the question here was like, okay, and if you really get bad reduction, whatever you do, can you specify more? What do you get? You know, for example, the two cases that I saw here, the two example, this one is a stable curve of genus 3. And this one, if I had add another node like this is also a stable curve of genus 3. So you can specify, even in the case of bad reduction, which type of bad reduction. And I mean, this in general for genus 3 is still work like in progress, but I mean, honestly, like very far away from being done. But for Ciani quartics, with my collaborators in this paper, plus Pinar Kilitzer and Sabrina Kunzweiler, we characterized, and that was a really nice work, we characterized the possibilities for the reduction type of a Ciani quartic just in terms of the invariance. So you look at the invariance that I presented to you before, you look at the evaluation of the invariance, and there is really like a criterion, like if this valuation is bigger than this, if this one is bigger than this, blah, 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 then the reduction type is this one. I mean, this is not the main work that I want to talk about, but I mean, it was really using what is called the admissible cover theory, in which, I mean, I just did the picture. I'm not going to explain it, but we just associate it to a curve, what we call the decorated graph. That is this thing, is how the ramification points that comes in pair collide. Then you do like some blow-ups. You consider this is like a cover, so you translate this from the P1 to the genus 3 curve, and I mean, you end up computing the reduction type. And this was really nice because, like, previous to this work, we only knew how to compute reduction types for genus 2 curves. That was a work on Liu. Vau and Bevers got explained how to do it in theory for superelliptic curves. And then the brothers Otkister, Céline Mestre, and Adam Morgan had worked out like the details for the hyperelliptic case. But as I said, the Ciani quartics, what is nice is that they are not a special type of superelliptic curves. So I mean, and in all those works, they used very strongly the thing about getting like this cover, this degree, well, cyclic cover to P1. So I mean, we had to use like different techniques. Okay, but that was the previous paper, and in this paper, in the 15 minutes max that I have, what I want to talk about is the conductor. What is the conductor? So the conductor exponent, because I mean, if you think about this, the reduction type, this is really like geometry, as I told you. It's really about, okay, maybe you need to go to a field extension and then you look at the reduction, but you don't care that much about the field in the sense that you are allowed, or you need even, to get to consider field extensions. So it's more like in the geometric perspective. But for the conductor, there is really this arithmetic component in the sense that it's like sensitive to field extensions. And it is a number that is information on the reduction type actually of the Jacobian, not really of the curve. And it's linked actually to the Galois representation associated to the Jacobian of the curve. It's an arithmetic invariant. For instance, just to give an application, elliptic curves, when you look at the classification of elliptic curves, the famous Cremona tables, for instance, the elliptic curves, they are ordered by conductor. is not by discriminant. It is actually the conductor what is important. I mean, well, this is very particular maybe to elliptic curves, but because elliptic curves over the rationals are modular, the conductor of the elliptic curve is related to the corresponding modular form. So this is, I mean, the conductor is like the interesting arithmetic invariant, not the discriminant, or not that much the discriminant. The thing is that there is a relation between the conductor, this is the conductor at P for the elliptic curve, is always smaller or equal than the evaluation at the prime that you are looking at of the discriminant. Well, I mean, the OC formula is more precise. It's not only an inequality, but I mean, this is a corollary of the formula. So what I'm going to give you, instead of giving to you the precise definition for the conductor, because it's kind of complicated and you have to go to the Jacobian, I'm just going to give you a formula to compute the conductor. And the idea is that, well, in our case, I'm going to consider now only the case in which the curve has potentially good reduction. But I mean, this can be generalized, no problem. It doesn't matter of the reduction. It's just because it's easier to present the result in this way. Then what we do is that we consider the minimal extension over which the curve has a model with good reduction. So I call this model wide. This, you can think this is a stable model. And then we get an axiom, a natural axiom of the Galois group of this extension on the reduction, on the special fiber of the model. So this is going to give us like a subgroup of the automorphism group of this curve. We can do the quotient and we get another curve. And another assumption that this is more difficult to control, but that we still know how to do it. If the extension was stamely ramified, then we get this formula. So the conductor of our curve is just twice the genus of our curve minus 2 times the genus of this curve set that we defined there. As a corollary, if you want, for Ciani quartics, we get that the conductor is one of these numbers, 0, 2, 4, 6. Basically, because it is between 0 and 6, and it is even. And something else that we managed to prove that this is not always true for general curves is that the curve actually has good reduction if and only if the conductor is 0. So if the curve has good reduction, then the Jacobian has good reduction, and then the Néron-Safarevic theorem tells you that the conductor is 0. But the reverse implication, having that the conductor is 0, not always implies that the curve has good reduction. But we managed to prove this for Ciani quartics, for instance, by using this formula and by studying the possibilities for the reduction type. So the last ingredient before presenting to you our results on the conductor of Ciani quartics that I need to give you is, well, I mean, I presented the invariance for Ciani quartics, and you know how to compute the invariance of a Ciani quartic. I gave you the formulas, but now we ask ourselves like the opposite question. If I give you some invariants, can you give me a Ciani quartic with those invariants? Because if you want a little bit, maybe I want to fuss about that point. But one of the motivations to compute the conductor of a curve, and I come back here to the case of elliptic curves. So one of the motivations is like to produce tables or lists of curves ranked by conductor. So what we would like to do is, like, for instance, to be able to compute all the Ciani quartics with conductor smaller or equal than something. And how do you do that? Like, I mean, you don't know, but if you get an inequality like this one, and then you know how to construct Ciani quartics with given invariance or with given discriminant, then you would be able to do this. So somehow the idea is like what you want to do is like first to be able to construct curves with given invariance, and then like choose the invariance in an appropriate way, because there was this way of writing the discriminant in terms of the invariance, to get curves with given discriminant, and then if you have such a relation, so to construct curves with given conductor or with bounded conductor. So an important thing is like to be able to, given some invariants, to be able to see which curves you get with those invariants. So this ingredient, well, I mean, this question, we handle it in the following way. We have this theorem that says, okay, take your field. Again, think about a discrete valuation field. In my mind, I always have QP. But you can think also about, I mean, I don't know, if you prefer a more geometric setting, you can think about Q double square bracket T. You know, you have a family with a parameter and you're going to make the parameter equal to 0, as you prefer. So you fix the value of your invariance. You assume that you start with something that in theory gives you a smooth curve. So with discriminant different from 0. You defined L, the field extension, given by the splitting field of the polynomial that I defined before. So recall that the roots of that polynomial were like Matcal, Gothic, ABC. Assume first that P is different from 0. Then the curve that I'm showing you here in red, white one, has invariants, the ones that I'm showing here. So basically they are just a multiple of the invariants that you wanted. So basically they define the same point in the moduli space. So basically you got a curve with invariants that you wanted. Except that you got this annoying extra factor, P. So if the evaluation at P of your prime is 0, but it doesn't matter. So I mean, you control still what is happening at a given prime, but somehow you are adding. So the idea is in this way, you constructed a curve that isomorphism class was the one that you wanted. But in order to get an integer model of your curve, because I mean, you don't want to divide everything by P and adding denominators, you had to pay the price of increasing the discriminant of the curve. And not only that, also that this curve that I gave you, this Ciani quartic in a standard model, defined over L, is defined over L. That is a priori a field extension. The nice thing is that we can also give, for instance, in the case, assume that the degree of L over K is a multiple of 3. Then in that case, we can provide an isomorphism in such a way that defines a model that is defined over K. But there is another problem, that is that the price to pay in this case is that the discriminant now increased by another factor that is proportional to Q. So somehow the problem is that you started maybe with a nice set of invariants for which the discriminant was controlled. You didn't have very bad primes, but in order to get a curve with the given invariants and define over the field that you were interested, you may get like some extra factors. Well, I mean, I was assuming here P to be different from 0, but I mean, actually, if P is equal to 0, we gave a little bit different equation, but I mean, we handle the different cases also in a nice way. We have a general reconstruction algorithm. Okay, so now I can finally, 3 minutes, the last 3 minutes, I can state the result. So for our results, we have like some assumptions, but as I said, they are not really like really crucial assumptions. We can kind of remove them. It's just as the computations at some point became like really messy, and we prefer just to simplify the results and give them like in the generic case. So generic case first is like P greater than 3. This is because of the extensions that we were playing with. The Galois group is a subgroup of S3 that has cardinal 6. So we want to avoid the divisors of 6. We take our invariants that we assume normalize. I didn't talk about this condition, but this is just don't take all the invariants with positive valuation, because this is kind of multiplying by P everything and then you get bad things. Assume potentially good reduction and the curve to be non-special. This is easy to control. This is, as we mentioned before, you just look at invariant Q. And then with all those conditions, we characterize in the following way the conductor. If the curve has potentially good quartic reduction, which is totally characterized just in terms of the evaluation of the invariance, is the conditions that you get here. Then there are two cases, depending on the evaluation of Q to be 0 or different from 0. But in the two cases, we prove that there exists a model, a standard Ciani model, so not only a model, a standard one, Ciani model, defined over the field K, that is the field, I haven't said it. So, I mean, this is in P3K with weights 3, 3, 3, 6. So you have a model over K. In the first case, one of those models, you can even get it with trivial conductor, meaning with good reduction. But then the other twist, so basically a twist, in case you don't know it, is an isomorphic curve defined over K, but the isomorphism is defined over a field extension. So the arithmetic properties of both curves, they are not the same. And we see it here in this case, because you get that there is one with conductor 0, and for all the other ones, you get conductor 4. And in the other case, the case with positive valuation for Q, you always get conductor 4. And then in the case of potentially good hyperelliptic reduction, that is characterized by some valuations of the invariance, then you get the following result. We also prove the existence of a model defined over the base field, and all the twists of this model, they have the same conductor, is equal for all of them, and is equal to the number that appears here in the table, depending on the parity of E. The E is defined here, and depending on the degree extension of L over K. L is the splitting field of the polynomial P. That, by the way, we also give like an algebraic, you don't need to compute the field. We also give an algebraic characterization. And as a corollary of this result, we get an inequality in the direction of the OG formula. We prove that, well, under all these conditions, the conductor is indeed bounded by the evaluation of the discriminant of the plane quartic, which goes, as I said, in the direction of one day being able of producing this list of Ciani quartics ordered by conductor. Just to finish, if you allow me, since we started a couple of minutes late, this is, I promise, is the last thing. It's just a naive example, like with everything that I explained. A natural question is to say, oh, but can we already use like this reconstruction algorithm, those invariants, this control of the conductor to get, like, for instance, a curve that we know that there is only bad reduction at a given prime. And let's say that this prime is 2. And because the discriminant is the product of those invariants, you can say, oh, I'm going to make all these invariants equal to 1. And now, because I know that the price to pay is that there is a P, a factor P appearing in the discriminant, I'm going to take this invariant equal to this number in such a way that force P equal to 1. So there are no extra primes appearing. But then when you do that, you have to consider this Gothic P polynomial, the splitting field, the discriminant of that polynomial. And even if you were trying to get something small, you get this factor. So you get this big factor Q. And then, well, basically you get, even if you were trying to get only 2's in the conductor, by only getting 2's in the discriminant, well, but you got this extra big prime, and then like for the curve defined over the rationals, having those invariants, well, but you get this ugly discriminant, so much bigger than what you were expecting. And I mean, if you look at the criteriums that I showed you before, then you get, yeah, that indeed, you get conductor equal to 4 for this annoying prime. So yeah, I mean, it's still a little bit complicated how to use in practice the results. But well, I mean, this is nice. So many other things to do in the future. So thank you very much for your attention. This is all.
Okay, thank you very much for the nice talk. So let's thank our speaker, maybe in the chat. So are there any questions for Elisa?